Namaskaram. In last class, we have seen what is the concept span in a vector space, and what are the some simple properties of spanning set. Spanning set is nothing. It is a representative of a vector space or a subspace. In this session, we will discuss about the concept linearly independent and dependent sets. Okay. Okay. First of all, we will define the concept linearly dependent. What is the definition? A set of vectors v1, v2, etc. vn in a vector space V is called linearly dependent if there exist scalars c1, c2, cn. Not all of them are zero. That is very important. Not all of them are zero, such that it's linear combination. That is c1, v1 plus c2, v2, etc. plus cn, vn equal to zero. That's the idea. Okay, this is very important. Not all scalars are not equal to 0. Maybe some c1 equal to 0, maybe cn equal to 0, no problem. Not all of them equal to 0. Right? Then only we can say that given set is linearly dependent. Okay, I will show you an example. Okay, consider this example. This is our v1, 1, 1, and this is our v2. We consider two vectors, 1, 1 and 3, 3. That is belongs to R2. This is our vector space V. We have to check whether they are linearly dependent or not. That means C1 V1 plus C2 V2 equal to 0, provided not all Ci's are 0. Not all C1 and C2 are 0. Does there exist scalars C1 and C2, not all of them 0, satisfying this condition for these two vectors? Yes, there exist. Minus 3. What is our V1? V1 is 1, 1 plus 1 times. What is V2? V2 is 3, 3. It's clear that this sum is 0. 0 means 0 vector, 0, 0. Right? 0 vector in the vector space. In R2, our 0 vector is 0, 0. So, what is our conclusion? Here, not all CIs are 0. Actually, here C1 and C2 both are not equal to 0. It's okay, that's good, no problem. So, this set 1133 is linearly dependent. You got it? You will see one more example. Okay, before that, we have one more definition, that is linearly independent. What is linearly independent? If it is not dependent, then linearly independent. That's all. Okay, that is the definition of linearly independent set. Okay, suppose a set is not linearly dependent. Non linearly dependent means what? Dependent means there exist scalars c1, c2, cn such that not all of them 0 equal to 0. If it is not dependent means what? This condition is violated. Not all 0 means all. What is the opposite of not all 0? All 0. That means c1 v1 plus c2 v2 etc. plus cn vn equal to 0 implies what? Implies all 0. All 0 means all the CIs are 0. This is the condition for linearly independent set. Actually, they are opposite definitions. That means if it is independent, never dependent. If it is dependent, never independent. Because the definitions are just opposite. Clear? So this is the idea of linearly independent set. Again, what is linearly independent? A set of vectors v1, v2, vn is called linearly independent if c1, v1 plus c2, v2, etc. plus cn, vn equal to 0 implies all the scalars are 0. Then we can say that this is independent. Suppose there exists at least one set of non-zero scalars like this one, not all zero scalars, then we can say that it is dependent. Okay, let's see another example for linearly independent set. Okay, we consider a set 1, 0, 1 belongs to R square. And what about this set? This is our V1, this is our V2. We have to check whether it is dependent or not. Okay, for that we consider our linear combination C1 V1 plus C2 V2. That is C1 into 1 0 plus C2 into 0 1. Right? And what about this one? We assume that this is equal to 0. 0 means 0 0, 0 vector. And what about this one? This is nothing. C1 comma C2 equal to 0 0. This implies what? So we are starting from this one. This one means C1 B1 plus C2 B2 etc. Cn Vn equal to 0. This implies C1 comma C2 equal to 0 0. This implies by comparing the coordinates we have C1 equal to 0 and C2 equal to 0. That means all the scalars are 0, right? There is no other option. Okay, if at least one CA is non-zero, then this linear combination is not equal to 0. So that's why this is not linearly dependent, or we can say that this is linearly independent. So this is the idea of linearly independent. Okay. Okay, first problem. Determine whether the set 1, 2, comma 3, 6 is linearly independent or not. Okay. What about your conclusion about this set? Is it dependent or not? That means the question is is it possible to find non-zero scalars C1 and C2 such that uh, this linear combination equal to 0? If there is no non-zero scalar satisfying this condition, then we can say that independent. Okay. If non-zero scalars exist, then this become linearly dependent. So what about this one? Is it dependent or independent? Does there exist C1 and C2? Non-zero C1 and C2? Yes, it is exist. What is our C1 and C2? Similar to the previous case, here C1 is, oh sorry, this is 1, 2, not 1, 1. Okay. So what about C1 and C2? Yes, there exists a non-zero scalar C1 and C2. Yes, if we choose C1 equal to -3 and C2 equal to 1, then this sum becomes 0. Here 0 means 0 vector. Okay, that is 0, 0. Does there exist? Okay, so what about this set? It is linearly dependent, not independent, right? Does there exist another pair of C1 and C2 satisfying the same condition? Suppose C1 equal to 1. That means 1 into 1, 2. Plus, what about C2? C2 into 3, 6 equal to 0. Is there exist? Yes, that is minus 1 by 3. This is a scalar. Minus 1 by 3 is a scalar. It's a real number. So minus 1 by 3 times 3 become minus 1. This is minus 2. Again, sum equal to 0. So these scalars need not be unique. If it is dependent, then scalars need not be unique. Yes. At least there exists one pair of non-zero scalars. So this is another pair of scalars. Anyway, this is linearly dependent, not independent. Okay. Next problem. Determine whether the set t square plus 2t minus 3, t square plus 5t, comma 5t square minus 4 is linearly independent or not. Okay, this is not direct because this is not a trivial example. But in the previous case, it is very trivial. You can easily identify the scalars by observing this set. Okay. But in this case, this is not trivial. So we have to apply a systematic method. What is systematic method? We have to check whether does there exist non-zero scalars C1, C2, C3 such that this is equal to 0, linear combination equal to 0, or this equal to 0 implies all the scalars are 0. Okay, that's all. So we assume that this is equal to 0. Okay, then we have a system of equation. How? By comparing the similar terms. So next we are going to compare the terms containing t square and terms containing t and constants. So what happened? So this become, okay, so by comparing the terms of t square, then its coefficient is like this. Similarly, this is the expression. And 0, 0 means what? 0 polynomial in actually all the members from which space? They are from, sorry, that is P2. Okay. So what is the general element? What is the 0 element in P2? That is 0 plus 0t plus 0t square. This is the 0 vector in our P2. So you can compare the similar terms. Similar terms means coefficient of t square, coefficient of t and constant term. What is coefficient of t square? That is C1 plus C2 plus 2C3. And what about the coefficient of t square in our RHS? That is 0. Okay, so 0. So now you have three system of equations. Okay. Oh, sorry, one system of equation containing three equations. Okay, we have three equations. That is nothing. That is a system. That is a linear system of equation. We know how to solve a system of linear equations. We can convert this is of the form some ax equal to 0 form. Okay, what is our x? X is nothing. C1, C2, C3. So our aim is to solve this linear system, or we have to find this x. If x equal to 0, x equal to 0, then we can say that all the CAs are 0. That means our system is linearly independent. If x is non-zero, then we can say that the system is dependent. Okay. So you can solve the system either Gauss elimination or some other method. Okay. If system has only zero solution, then we can say that it's a trivial solution. Okay. And also from matrix calculus, there is a shortcut for identifying it has a zero solution or non-trivial solution. That is in terms of determinant. If det of a equal to zero, then system has infinitely many solutions. That means non-trivial solutions. If det of a is not equal to zero, then system has only zero solution. Okay. So you can either you can solve the system using Gauss elimination method, then check whether it has a zero solution or non-zero solution, or you can test it has a unique or infinite. Unique means only zero solution. Okay, this is unique. Unique means only zero solution. Otherwise, it has infinitely many. That means non-zero solution by checking its determinant. Okay. Anyway, we can solve for the system, and we can conclude that this x equal to 0, 0, 0, 0. That means C1 equal to 0, C2 equal to 0, C3 equal to 0. So what is our conclusion? So by solving the system or using this concept, we can identify that the system has only zero solution. So our system, so this given set of three vectors is linearly independent. Clear? So the system of equations and its properties or its solutions play a good role in linear algebra. So all of you should familiar with the system of equations and how to solve system of equations. Okay, or this system of equations and matrices, they are the basis of linear algebra. Okay. Okay, another result is a set of vectors is linearly dependent if and only if. It's an equivalent criteria, that's why if and only if. At least one vector in a given set is a linear combination of other vectors. Okay, if it is dependent, this is happen, or conversely, if one vector is a linear combination of other vectors, then we can say that the set is linearly dependent. This is very important characterization of linearly dependent set. Okay, and there's a remark. It is not necessary for every vector in a given set to be a linear combination of other vectors. Okay, because this result says that at least one vector, that's all. At least one vector is a linear combination of rest of the vectors, not all of them. That is his remark. Okay. Okay, let me explain this with an example. You consider this set 1 0 3 0 0 1. What about this one? Is it dependent or not? That means okay, that means C1 10 plus C2 30 plus C3 01 equal to 0. Does there exist a non-zero scalars or all of them 0? It's a very simple example. You can easily observe what is C1, C2, C3. Yes, if you choose C1 equal to -3 and C2 equal to 1 and C3 equal to 0, then this linear combination is 0. Clear? So what is it? 0 means 0 vector. Okay, 0, 0. So what is our conclusion? Here, not all CAs are 0. That is very important. Not all CAs are 0. Okay, here C3 equal to 0. That's okay. That's not a matter. Here C1 and C2 are non-zero. So what is our conclusion? This set is linearly dependent. Right? Because not all of them are 0. If all the scalars are 0, then only we can say that it's a linearly independent set. Okay, so this is satisfied. This is a linearly dependent set. Then what about the result? The result says that at least one vector is a linear combination of rest of the vectors. Okay, what about the first one? Is it a linear combination of rest of the vectors? This is our first vector, and what are the rest of them? These are the remaining vectors. My question, is it a linear combination of these two? Yes, possible. We can write 1 0 as a linear combination of these two. Why? We can write like this 1 by 3 of 3 0 plus 0 times 0 1. Now this 1 0 is a linear combination of these two. Okay, similarly my question, so this condition is okay, at least one. Yeah, at least one is possible. Okay, for our interest, what about next one? Is it possible? Second one, 3 0. 3 0 is a linear combination of remaining means these two. Is it possible? Yes. 3 into 1 0 plus 0 into 0 1. And we have one more vector, that is 0 1. What about 0 1? Is it a linear combination of rest of the vectors? This is our last vector. My question, is it possible to write this one as a linear combination of remaining? Remaining means these two. Is it possible? Sum C1 into 1 0 plus C2 into 3 0 gives 0 1? Never. Whatever be the linear combination, here the second coordinate is always 0. But in this vector, second coordinate is 1. So this is not possible. There is no C1, C2 satisfying this condition. Right? So that is this remark. The remark says that this is possible if it is linearly dependent, and this is possible at least one, not guaranteed for all the vectors. Okay, this is not true for every vector. That's it. Okay, another important result is a set with a single vector. Okay, suppose you think about a singleton set U. A set with a single vector U is linearly dependent only when, if and only if U equal to 0. Very important result. That means a singleton set is linearly dependent if and only if U equal to 0. And what is the meaning of this 0? Is it our number 0? No, because U is a vector from some vector space. So 0 is nothing. The 0 is the 0 vector in the corresponding vector space, because U belongs to some vector space V. So this 0 also belongs to that V. Okay, that means this 0 is a 0 is not a number, it is a vector, 0 vector in that vector space. We know that all the vector space contains a 0 vector. Okay. Okay. Next example. It's a very important result. It's a very important result. A subset of a vector space V consisting two distinct vectors is linearly dependent if and only if, the if and only if criteria, equivalent criteria, one vector is a scalar multiple of other. Okay, so first we assume that our first condition, first statement means two distinct vectors. We can choose some u1 and u2. u1 and u2 are two distinct vectors, and we assume that they are linearly dependent. This is our assumption, and then we have to show that one of them is a scalar multiple of other. Okay, this is our assumption. So that's our first side. First we have to assume the first statement, then we have to prove second one. Similarly, converse is also true. That means we have to assume the second one, then we have to prove the first one. So we consider u1 and u2 belongs to V, and we assume that they are dependent. So what is the meaning? The resistor scalars C1 and C2, not all of them 0, such that C1 u1 plus C2 u2 equal to 0. 0 is a 0 vector in that vector space. Okay, the guarantee is that not all the CIs are 0. At least one CI is not 0. At least C1 equal to not equal to 0, or C2 not equal to 0. Maybe both are not equal to 0. No problem. Okay. Anyway, we assume that C1 is not equal to 0. We know that at least one of them is not equal to 0. We assume that C1 is not equal to 0. Then we can rewrite this expression as u1 equal to minus C2 by C1 into u2. Now it is clear that u1 is a scalar multiple of u2, and this number is well defined. Why? We assume that C1 is not equal to 0. So this is a well defined number. So u1 equal to some scalar into u2. Okay, so this is true. One of them is a scalar multiple of other. Similarly, suppose C2 is not equal to 0. Suppose C2 is not equal to 0. Then you can we have a similar result. u2 equal to some scalar into u1. Anyway, whatever be the case, one of them is a scalar multiple of other. Okay, so what is the converse of this result? We assume that one of them is a scalar multiple of other. Then we have to claim that the set is linearly dependent. Okay, so we assume that one of them is a scalar multiple of other. Okay, that means assume that one vector, let it be u2. u2 is a scalar multiple of u1. We assume like this, or u1 equal to some beta times u2. Whatever we no problem. Anyway, we assume that one of them is a scalar multiple of other. Then we have to show that they are linearly dependent. Okay, and also this, we assume that this alpha is a non-zero scalar. Okay, so what happened? Okay, if it is 0, no problem. If it is 0, then both the vectors are 0. We know that 0 vector is linearly dependent, no doubt. Okay, anyway, whatever with the scalar alpha, no problem. So this is C1 U1 plus C2. Okay, our question is, does there exist non-zero scalars C1 and C2 such that C1 U1 plus C2 U2 equal to 0 for this particular U1 and U2? If U1 and U2 satisfy this condition, we have to show that they are linearly dependent. That means, does there exist a non-zero scalar satisfying this condition? Is it possible? Yes, it is possible. What is C1 and C2 such that its combination equal to 0? Yes, if we choose C1 as minus alpha, alpha is a real number. So minus alpha is also a real number. Minus alpha U1 plus what is C2? Because our U2 is alpha U1. So we can choose C2 as 1. 1 into U2. And what about this one? This is nothing. Minus alpha U1 plus what is U2? U2 is alpha U1. So this becomes 0. So it is possible to choose scalars if alpha equal to, of course, if alpha equal to 0, then they are automatically linearly dependent because both the vectors are 0 vectors. We know that 0 vectors are linearly dependent. Okay, so here we assume that alpha is not equal to 0. So alpha is not equal to 0 means this is not equal to 0 and this also not equal to 0. Okay, anyway, at least one non-zero element is there. So this linear combination equal to 0. So the conclusion, these two vectors, which vectors U1 and U2 are linearly dependent. Okay. So anyway, this is a very important result. We have to check whether if two vectors are dependent or not. Suppose it's contains of two vectors, then we have to check whether if both are 0, then okay, it is dependent. If it is non-zero vectors, then check whether one of them is a multiple of other or not. For example, you consider 1, 2 and 3, 6. It is clear that here this 3, 6 is nothing. It is 3 times 1, 2. That means one vector is a scalar multiple of other. So no, they are linearly dependent. Okay, you think about another one. 1, 1 and 1, 0. If they are multiple or not? Never. Whatever be the scalar, alpha into this is never equal to this one. Right? Or similarly, some scalar into 1, 0 never equal to this one because here the second coordinate is always 0. So that means these two vectors 1, 1 and 1, 0 is linearly independent. Clear? So if for two vectors, because it is not dependent, then it is independent. That's why. So if for two vectors, one of them is a scalar multiple of other, then we can say that linearly dependent. Otherwise, that means otherwise means one of them is not a multiple of other. Then we can say that they are linearly independent. This is an important criteria for independence and dependent for a two element set. Okay, these are some useful results. If a set of vectors S in a vector space V is linearly independent, then any subset of S is also linearly independent. Okay, that means we consider a vector space V. Okay, this means we consider a vector space V and also we consider a subset S which is linearly independent. Then the result says that any subset of S is also linearly independent. Any subset of S. Okay, very, very useful result. And similarly, we have one more concept. If a set of vectors S is in a vector space V is linearly dependent. Okay, so a set of vectors S in a vector space V is linearly dependent. Okay, so here there is our vector space V and we consider a subset S and S is linearly dependent. Then the result says that any larger set containing S is also linearly dependent. So these are two useful results. That means as a in general, this means a superset of a linearly dependent set is always linearly dependent, and this is says that subset of a linearly independent set is always independent. Okay, these are very useful results. Anyway, they are easy to prove. Anyway, they are useful. Okay, that's it about this session. In next session, we will discuss another concept that is called a basis. Basis is defined using the concepts span and linearly independent. So we will use both these concepts in next session. Okay. Thank you.